Hello and welcome to this first video in what will become quite a long series of tutorials on the amazing and beautiful topic of calculus. I've been sort of heralding this set of tutorials in the last few tutorials on functions because particularly as a scientist, as a physicist, calculus is the game changer in terms of how mathematics has been applied to the world around us, particularly through science. The creation of calculus in the late 1600s was an absolute game changer. A metaphor I sometimes use with my students is to say that, just a picturesque metaphor in a sense, that if you think of using mathematics to understand the world around us as being some kind of struggle, then pre-calculus we had weapons like bows and arrows and spears and maybe a slingshot, but then everyone stood still when they heard this rumbling in the woods and the sound of trees crashing, and out of the woods comes this enormous World War II tank blasting shells, and that was the arrival of calculus on the scene in terms of the utility of mathematics to describe the world around us, but also actually in completely transforming many areas of mathematics as well. So, what I'm going to do in this first tutorial is actually motivate calculus rather than simply introduce it mathematically. I will do that in the next tutorial, but because it's such an important subject, I really want to spend 10 minutes here motivating it so that everyone can see, well, why do we have calculus? I feel that calculus is often taught in schools as a rather dry subject. Essentially, here's a toolkit, here are some tools, here's how you use these tools, and it's often taught as a set of rules, which can leave students feeling very perplexed because they may have heard of calculus and thought, oh, I can't wait to make that transition from sort of a pre-calculus understanding to a calculus understanding, but they may then be left feeling rather disappointed because they just learned a few rules. And my aim really in teaching this is the following. There shouldn't be this big transition in mathematics education between pre-calculus and calculus. It's such an important subject that really every student who is beyond the most elementary of mathematics should have an introduction to calculus, particularly in terms of why we have it and why it is so useful. The subject often gets bogged down in lots of technical details. I will not be doing that anyway in these tutorials because at this stage of mathematics there's no real need to get into quite formal concepts and technicalities, although those are absolutely important in mathematically proving the rigor of calculus. But that's usually something that you can deal with maybe in a year or two's time at a slightly more senior stage of education. Right, so let me motivate calculus. It stems from this concept that we have been discussing in recent tutorials of the idea of a function. And we thought of a function, first of all, in quite mathematical terms, as a mapping from one set of real variables x to another set of real variable y, and a given element of this set we would call x, and a given element of this set we would call y. And we talked about this idea of a function that maps a value of x onto a value of y. And that is actually quite a formal way of thinking. So there's that mapping or function, f of x from x to y. So the value y is the outcome of applying the function f to x. A more sort of metaphorical way of thinking about this, which I think has the utility that it gives you more of a sense that you're actually actively doing something with an input and an output, is to think of the function as a machine. We talked about this a little bit. So it has a great big F plastered on the side, has a tube to the left and a tube to the right, and there's all sorts of machinery going on inside that we don't have to worry about. But essentially you put an object x in, and out comes f of x, a number that is the result of applying this machine to the input x, and let's, for the sake of argument, call that y. Now, certainly this idea of a function is a very, very useful idea in thinking about the world around us. You could, for example, I think I gave this in the first tutorial on functions, think about how does oxygen concentration decrease as we increase in altitude. And you could imagine increasing your altitude, measuring the oxygen concentration, and writing down a table of numbers, altitude every 100 meters, oxygen concentration decreasing. And that table is sort of like a telephone directory. You can sort of look up the input, which is altitude, and the table gives you the output, which is, in that example, the oxygen concentration. The function is the relationship between the two, and you can imagine maybe plotting that data on a graph or having some scientific model of how it should be, that you would actually have some functional relationship between, in that example, altitude and oxygen concentration. And there are many, many such applications in the world around us where you can think about a table relating an input to an output. The point, though, is this. It turns out that in much of science, in most of physics, in much of science, in much of economics, that idea of an input and an output is not quite the key idea. It just needs a little tweak to make it a really key idea, and then we need, as we'll see in a second, to think of a slightly different kind of machine. So what is this idea lacking in terms of an input and an output? What it's lacking is that the thing we're usually most interested in is not in what output is connected to an input, but the question we're most interested in is the following. What would be the change in an output given a change in an input? So, for example, you might ask as an economist, if I change the interest rate, how will that change inflation? A biologist might ask, if I change the population of predators in this ecosystem, how will that change the population of prey in that ecosystem? A physicist might say, if I change the rate at which an electric field is oscillating, how will that change the rate of a magnetic field oscillating? It's that idea of change that is really most often the central thing that we're interested in. And why is that? It's because we tend to exist in quasi-stationary environments. Our environments are not chaotic. They tend to be relatively stable, but there are changes. So we're not always interested in the state of things as they are. We're interested in how will the state change given the change of some other parameter. Now, let's just help ourselves symbolically here by introducing this symbol delta. I think I might have mentioned this a couple of times in earlier tutorials. This symbol is a capital or uppercase delta, which is the fourth letter of the Greek alphabet. It's used in mathematics a lot to be shorthand for the phrase the change in or the difference in. Let's call it the difference in. Or the change in. Depends slightly on the type of sentence that you're trying to construct mathematically. And so here then is a different kind of machine. I'm drawing it as a more nebulous object. I'm not going to put a big label on it quite yet. It still has, though, a input and an output. And what's being fed in now is the input is not, say, x. It is a change in x. And the output will be a change in, and I'm going to write f of x. So I'm imagining that there is a variable y still in the background that is the outcome of applying a function to x. And the machine above tells us for a given x what that value of y is. But now, knowing that this output has some functional relationship to the input, the rate of inflation will have a functional relationship to the interest rate. The prey population in the ecosystem will have a functional relationship to the predator population. The magnetic field will have a functional relationship to the electric field. Given that in the background, now the question is, if I change that input, knowing that that f of x is going on in the background, what's the change in the output? How is that change in the outcome of the function related to the change of the input? And the answer is by the derivative. That's the word we use, and I'll give it the symbol f primed. So I'm going to write down an equation which is essentially 90% of calculus. It sounds like a bold claim, but it really is. And if you understand this equation and are confident in utilizing it, you will be able to have so much confidence and comfort with calculus in terms of learning it, and see that, yes, there are formalities if you want to do it really, really precisely, but in terms of using it as a tool, it is actually a very robust piece of mathematics that comes down to the following statement. The change in an output, this change in the function, the value of the function, is related to the change in the input. It is proportional to that change in the input. And the constant, the object that is the proportionality here is what we're going to call f primed. Yes, that was a Freudian slip there, calling it constant of proportionality. That's just a very common phrase. What I mean to say is that the thing that makes this into an equation, turns this proportionality into an equation, is this other factor, f primed. And we call this the derivative of f of x. And that's the first piece of important terminology that we'll have with this motivation of calculus. The derivative is the central kind of foundation that connects the change of an input to the change in an output. And much of calculus, as you'll see as we go forward, is essentially around calculating for a given function or for a given problem what this derivative is. Because if you can calculate that, then you can relate, as I've said a number of times, change in an input to change in an output. So what we'll do in the next tutorial is introduce this a bit more mathematically, looking at graphs, in fact, because it's when you look at graphing functions that you can get a very nice, simple geometrical interpretation of this derivative. But I think it's actually better to start from here so that you know that the derivative is not just something that you can pull off a graph. It's actually amazingly powerful to know whenever you are trying to relate the change in one thing to the change in another. And before calculus, it is quite simply the case that people did not have a way to connect these things. And so in a sense, you could almost argue that mathematics and science could only look at stasis. They couldn't really look at change in a meaningful way. But with calculus, all of a sudden, change was something that could be quantified and engineered and understood, and that really transformed particularly physics, but also has great application in chemistry, in biology, in psychology, in medicine, in economics, and so on, and so on, and so on. So the word calculus has the same root as the word calculate. It should really be thought of as this tank that comes out of the woods into the clearing and transforms the battle of using mathematics to understand the world. It is an absolute game changer because all of a sudden you can calculate change. And this equation here has so many utilities in demystifying much of the baggage that calculus has that often seems to turn it into rather a dry and perplexing subject. So if there were one thing to take away from a course in calculus, it would be this equation that the derivative relates the change in the input to the change in the output. And our job as scientists and mathematicians is for a given function to work out what this derivative is. And that's what we'll start to talk about in the next tutorial. So I hope this sort of motivation to calculus has at least been helpful in the sense of maybe, giving you a sense of excitement in going forward with this topic, that it is not just some dusty, dry subject in a maths course. It is a point of view that can transform the way that you think about the world and give you tremendous power in actually calculating aspects of the world around you, given that most things that happen are a result of change. Right, thank you so much for your attention. I hope this has been interesting, and I will see you for the next tutorial, which will be a more formal introduction to calculus. See you then.